No worries.
See, this is why you need people hiding in the background to keep me right. Okay, so recording is now started. So I won't need to say all the bit about who I am again. What I'm going to do this afternoon is take you through some of the functions of SPM. I'm going to imagine that we've got some functional imaging data that we want to process. I'm going to step through it a little bit, but we'll have a bit of a play around with SPM first, just so that you understand which buttons go where. So what I'm now going to do is to try to share my screen, which I hope is going to do that. And then I'm going to do that. And so hopefully at the moment what you should see is my as a normal MATLAB window. I'll keep going because obviously I can't see comments that easily at the moment.
We can see it, yeah.
Sorry, say again?
We can see your MATLAB window, yes.
Perfect, thank you very much. I will try to stick the comments outside somehow. Let's see if I can do that. And then do and I put comment, and if I try to do that, there we go. Right, so hopefully I should see the comments inside and the MATLAB window in the middle for the rest of the window. So first things first are that we need to tell MATLAB where the various functions are that are entailed or included within SPM. I happen to have downloaded and unpacked the SPM functions into this particular path here, documents, MATLAB, SPM, and 12, because that's the most recent version. So I'm assuming that you've done that a little bit before in some of the previous 6 videos, 6 sessions. So first thing we need to do is basically tell MATLAB where SPM 12 is. So far, relatively straightforward. To get SPM going, we type SPM. In terms of where MATLAB is, at the moment, I'm sitting in a folder. I've called it working. That's because I have the original data and a working set of data, just in case I get things wrong. You don't need to add this path to MATLAB, just the path to the general SPM is fine. So what we would to do to start SPM itself, just type SPM and it'll pop up a little window that has some selections, options that you might want to use. PET, VBM, MEG, or EEG, and fMRI. Obviously, depending on which particular flavor of data that you've got, you'll click the relevant button. Quite a lot of the functions are shared. It doesn't make a massive amount of difference, but if we're going to be consistent about things, I'm going to click on fMRI because that's the kind of data that I've given you. If you want to follow along as we're going, it takes a little while to pop up, and it pops up 3 separate windows. We have one in the top left, that's the green color, that has all of the a lot of the functions that are available, functions that have been described by some of the standard image processing algorithms like realignment, co-registration, normalization, which is the spatial pre-processing, which is in the top of the box with the green background. The next step down is tells you about model specification, review, and estimation. So essentially, there are 3 steps to any computational neuroimaging task. One is the pre-processing, which might involve a number of different things. The second is model specification. Model here is just setting up the statistical test that you want to do. You might be wanting to do a t-test. You might be wanting to do a correlation. In functional imaging, you're usually looking at a task compared to a resting state. So first you have to do some statistics at the individual level to test differences between task and task and rest. So that would be our first level statistics. And then once you've done all of the first level or within the individual statistics, then you would move on to the second level, which is where you would compare 2 groups of people, if it was a t-test, or correlate the results from your individuals with some external measure like age or BMI, something like that. And then at the bottom is the results button, which is the most useful one, which is the one that actually gives you the answer to your question. And the overarching question that SPM does is where. SPM stands for Statistical Parametric Mapping. A map tells you where. It doesn't matter if it's a 2-dimensional map of the streets of Aberdeen or a 3-dimensional map of a brain. The answer to the question from SPM is where. So that's the where is something happening, where is there a correlation, where is there a difference. And we happen to be looking at fMRI, which is here. We could have been looking at PET data, or we could be looking at EEG, stroke, MEG. The answer to the question is still the same. SPM tells you where. So what I'm going to do first is do something really simple, and I'm going to use the display button to display an image. So when you click on the display button, it pops up a file selector, or image in this particular case. If you are following along with this, be aware that you just need 1 click in SPM. So if I single click on the 3-key image and then go down to click the done button down here, what it will do is it will pop up a 3-key structural image. And you can see that it's in coronal, sagittal and axial views in the top of the window. And in the bottom half of the window, it gives you some information about the voxel size, the origin, and the dimensions of the data. What you can also do is click around in the data. So I'm just clicking with my mouse somewhere in one of the images, one of the views, and it automatically moves the other 2 to match. Okay, so that lets you just click around, make sure that you've got the data that you think you've got. If you look at the bottom left-hand side of this window, there's a button there that says Origin. Which corresponds to the location down here. The origin is defined in the header of the nifty image that we're looking at. Unfortunately, the origin can be the origin of lots of problems with SPM. Sometimes if that origin is not defined correctly, the nifty header, it will mess up lots of your other pre-processing, post-processing steps further down the line, it's always useful to check where the origin is in your data. It should be more or less, it should be centered in the left-right direction, and should probably be up here somewhere, maybe in the AC, anterior commissure. It's just kind of about there somewhere. That's where it's expected to be in all of the built-in functions within SPM. If it's not exactly there, like in this example, that's okay. If it's out by a few millimeters, that's okay. If you click on the origin button and it ends up out here somewhere, that's going to be a problem, because another image might have the origin in the correct place, and then SPM will struggle to match the two sets of data. The other thing about SPM is that it tries very hard to show you the nicest picture it can. And by that, I mean that if you display an image, it will do its very best to display it in the correct orientation and have the image in the middle of the boxes that you can see in the window. That doesn't mean that the origin is in the right place. You can still have a very nice image, but the origin can be down in the bottom left-hand corner somewhere. So it's always useful just to double check where your origin is, and if it's not in the right place, you can, using the translation options down here, move the image. I don't know if you noticed when I put in 10, it moved the image right by 10 millimeters. You see the sagittal view moving and the crosshairs and the coronal view moving. You can rotate the image in radians if you want. And you can resize. I'm going to cheat and do a resize of a -1, which is actually swapping the direction. Changing these numbers here in this table just changes what you're looking at on the screen. If you actually want to change the data that's saved on disk, then you need to click the reorient button, and then that will change the header that's associated with the pixel data inside the nifty image. Okay, so far we've done something not hugely useful. We've looked at a whole image. We can zoom in a little bit if you want. We can zoom in like that. You can apply that zoom to wherever you want. When I mentioned that that SPM is trying to show you the best possible image, it automatically applies trilinear interpolation when it's showing the both the data here and when it's doing any of its zooming. If you click onto nearest neighbor, you'll see that the image becomes slightly noisier. That's because trilinear and the other option, sync interpolation, tend to make the image smoother because it's taking data from across a wider range of pixels. Okay, so that helps us. That lets us see one picture, lets us check our orientations, lets us check our dimensions. you might have noticed down here that this image has a negative voxel size in the XY direction. In the X direction, I should say. Here, a negative voxel size means that the data is sampled in the opposite direction. So that essentially it means that the voxels are counted going from right to left rather than left to right. A negative voxel size doesn't, in this case, is not the size. The negative relates to the direction that the matrix is sampled in our three-dimensional matrix. Okay, let me use another button over here. This one is called Check Reg. It's a check registration button. They'll come in useful a bit later, but I'm going to use it to display two different images at the moment. And let me choose them the other way around. It doesn't really matter which way around you choose them. Just put one at the top and one at the bottom. So just as a bit of interaction, can anyone, let's see if we can find an area. Anyone tell me what they see that's different between these two images? You can either say out loud or type in the comments. I'll give you a clue. They're both of the same person. Anyone got any ideas?
The orientation?
Yeah, well, their orientation is the same. We still have coronal, sagittal, and axial.
No, sorry, the blue lines. It's just not in the same position.
Yeah, they're slightly. They're not quite co-registered, so they're slightly off. Yeah, so we've got a few. So position when the frame is different. Yeah, got a couple of suggestions of the resolution. So at the top we've got 3 Tesla MRI scan, and at the bottom we've got a 1.5 Tesla MRI scan. The resolution in these two images is very close to being the same. So it's not really resolution. They're both about 1 millimeter. I think that unless you're an MRI physicist, maybe the answer is not quite that obvious. The signal to noise ratio, I think, is maybe when you're thinking about resolution, it's the signal to noise ratio that you're looking at, or even the contrast to noise ratio. So in an MRI scanner, the signal is proportional to the field, essentially. So if you get higher field, you get more signal, but the noise stays the same, so you get better signal to noise ratio. So at the bottom, at 1.5 Tesla scan has a lower signal to noise ratio, which makes it look a bit noisier. And there's a better contrast to noise ratio in the 3T image. Contrast is the difference between the grey matter and the white matter in the brain. So the grey matter on the outside, that's the bit that does all the work. And then the white matter on the inside, that's the cabling. This is a structural scan, so we try to design these structural scans to give us the biggest contrast difference between the grey matter and the white matter. Anyone see anything else? I'll give you another starter for 10. How about these areas in the middle of the brain? Anything different about those? This is the same person. No. Do they look the same size or do they look different?
The ones in the top look bigger, but it's hard to tell because you don't know whether they're really aligned with each other.
Yeah. I'll try clicking around a bit just so that you can get an example. So come down a little bit. Let's see if I can find a good picture. So if we look at the top one, and sort of imagine that size. I'll try to find the same approximate location in the 1.5 Tesla scan. Let me see, it's probably about there somewhere. So yeah, so the one on the top, if we sort of squint a little bit and assume that they're kind of in the same orientation, the one at the top, the ventricles, so the grey black areas in the middle of the brain, they're bigger than they are in the bottom image. So anybody got any ideas what that might be? Think that's a good thing or a bad thing or just a thing?
Getting old.
Ventricles have got bigger. Yeah, that's exactly right. It's about, I don't know, 11 years difference between these two scans. So these two scans both happen to be of me. So in those 11 years, my brain has shrunk by a certain amount. As you can see that not only are my ventricles bigger here, but you can also see that sort of the gaps in the sulci are slightly bigger than they are over here in the down at the bottom in the 1.5 T scan. But I'm not worried about it because everybody's brain shrinks as we get older. It's just part of aging. But what this is a demonstration of is one of the things that you can use SPM for is that you can use it to measure how much shrinkage someone's brain has. I guess when we're probably in our mid-20s, give or take, our brain fits inside our skull pretty well. There's a minimum amount of CSF. Unless you have an accident, your skull doesn't really change shape, but your brain can shrink. And that's one of the things you can use SPM for. And that's to measure, it's called voxel-based morphometry. So it's a morphometric technique that lets you measure changes in volumes. So just an aside, in terms of allowing you to click around the data and see, and some of the things that you pointed out about being different slices, positioning being wrong within frames, those sorts of observations are useful, and we'll use them a bit later to check that some of the image pre-processing tasks have worked correctly. Because like most things, it might not work. Primarily, I found over the years is that the origin is in the wrong place. And that's why it's really good to be able to know what to expect. And if you find that you've applied a co-registration and you've got two sets of data that don't line up like they should, then you probably have to go back and start again. Okay, so what we're going to do is to go through the steps of a functional imaging study. I don't know if everyone knows how functional imaging works, but I'll give you a quick overview of how we use MRI to do functional imaging. So that the basic principles of functional imaging is that we use the magnetic properties of hemoglobin as an inbuilt contrast agent. Contrast agent is basically something that can change the brightness in an image. So in functional imaging, we'll give our individual a task, or a group of individuals a task, and we'll ask them to do that task for, let's say, 30 seconds. And then we'll ask them to stop and rest for 30 seconds, and then we'll ask them to do the task again. And we'll repeat that off and on process for 5 minutes, let's say, as an example. And what we're relying on here is that when an individual is performing the task, that part of their brain will be having to work harder than when it's not performing the task. And because hemoglobin and deoxyhemoglobin have different magnetic properties, that changing from rest to activation will change the brightness in that particular area of the brain. So if you remember, our question from SPM is always about where. So what SPM does is it allows us to find out where in the brain that change in signal is happening. And basically, we test all the individual voxels within the brain. A voxel is a volume element. It's a bit like a Lego brick. In our image, we've got our three-dimensional matrix, and each one of those is, you can think about it as a little Lego brick, and the brightness of that Lego brick is given a number, and then we test to see if that number in that location is bigger than we would expect at rest, or whether it's the same. And we did lots and lots of those tests. Remember, that's where we're doing our first level test. That can be our t-test. Is the signal brighter in this area or not? And if it's brighter, that means that bit of the brain is working harder, and therefore it's using more oxygen, and therefore the ratio of oxy to deoxyhemoglobin changes. So when we're collecting the data, we do really quick snapshots. And so if we have a look at this structural scan, and one at the top here, and 3 Tesla, it's a really nice picture. There's lots and lots of contrast, lots of high resolution. Each little voxel here is about 1 millimeter cubed. Let me display a functional image. So what I should say before I do that is that this image takes about 5 or 6 minutes to collect. This one that I'm now showing on the screen takes about 2 minutes to collect. Sorry, not 2 minutes to collect at all. It takes 2 seconds to collect. So you can see that it doesn't look very nice. It's you can just about tell it's a brain. You can't see any of the skull. Can't see any of the other tissue. But this image is sensitive to our changes in oxygenation. So the brightness in each one of these voxels, let me just show you what it really looks like. So the brightness in each one of these little voxels inside the brain, that will change depending on whether that area is activated or not. So here we're not really interested in the resolution or the anatomical location, or the anatomical information, I should say. We're interested in just in the brightness. Does the brightness change? So we take one of these snapshots, one every 2 seconds, and we keep doing that for 5 minutes. We'll build up a whole series of images, one after the other, and that will give us a time course. And what we want to do is we want to look at the same voxel, the same anatomical location, lots and lots of times across the whole time course. Now, even if you have the best behaved participant, over 5 minutes, they might move slightly. And if they do move, then we find, just like we had in the 2 structural scans, but the slices don't line up anymore. So the first thing that we have to do is we have to do something called realignment, which is basically just taking all of the subsequent images, take our first one as our reference, let's say, and all of the other images we want to realign so that they all line up with the first image. And that's called realignment. Estimate, which is where the program figures out how much movement needs to be applied. And then reslice is where we actually create a new image. If we just click on that button there, a window pops up, and this one is called a batch editor. So all of these buttons on the top left-hand side, if you press the button, a variation of this same box will pop up and allow you to add in the information that's required. SPM always tells you what it needs. If there's an X or an arrow and an X, that's telling you, I need information in here. Fill this in, please, before I can do anything. This arrow up here, it will stay gray until you've filled in all of the data. So let's just fill in some data because it's telling us what we need to do. It's even telling us what we need to click, which is new session down there. And we'll see up at the top, our arrow is now session. So in here, we're going to put all of the data, all of our functional data that we've collected once every 2 seconds for 5 minutes. So what we do is we click specify. That's the button that'll pop up a file selector. So it's telling us, it's giving us the opportunity, I should say, to select some data to put into that box in our batch editor. So we've got 3 files here, the 1.5T image, the 3T image, and an fMRI image. You'll notice they've got a comma and then a 1 after them. Nifty images can be packaged in different ways. You can have a 3-dimensional image, like we have here, with our 1.5 Tesla scan or our 3 Tesla scan. Oops, didn't want to do that. Go back. Or you can create a 4-dimensional image or a 4-dimensional file, which is what our fMRI image, or fMRI file, I should say, is. So the number 1 here means this is the first snapshot, our first image that we collected. Here they're called frames. It's just like taking a picture with your camera. But we're not interested in just the first frame. We want to take all of the frames that we're interested in. So what you can do to do that is if you type inf, short for infinite, it's now going to split up that 4-dimensional file into all of the individual snapshots. So see, in this particular case, we took 256 individual snapshots, and we want to select all of those. Now, to make things simpler, I'm going to use the filter and put an F at the beginning, and that's going to show me only the files that begin with F. And then I'm going to use another trick, which is right-click and select all. Oops. Hold on. Specify. speaking, and there we go. I don't know what happened there, but so right click, select all, and it says we've selected 256 images. If you want, you can scroll all the way down. If we just click done, what we'll find is that it's telling us 256 images. Slightly bigger. So what this function is going to do is it's going to take the first image in the list, the first snapshot in the list, and use that as our starting point. That's going to be our reference. All of the other images, 2, 3, 4, 5, 6, all the way up to 256, are going to be moved around until they match, so that they're all in the same spatial location. I'm going to do one change here, and I'm going to change that to the main image only, just because of it removes a writing step. And then you'll notice that because I filled in the arrow, the X over here, I have a green arrow, so we are now good to go. Push that button, something will happen, and we'll see a series of things happening over here. So it says registering images. So SPM is taking each image and matching it to the very first one in the list up here. We didn't have to pick the first one as the reference. We could have picked the middle one. It wouldn't have made too much difference. It's just doing the reslicing. Here it is changing the header, a bit like we had when we displayed the very first image. We had a series of 6 boxes with some translations and rotations. So what we've got here is, across the x-axis in these two graphs, we've got the image number, 1, 2, 3, 4, 5, 6, all the way up to 256. And along the y-axis, in the upper graph, we've got millimeters. So that gives you the distance that each image had to be translated till it matched our reference. And in the second graph, it gives us the degrees, the amount of rotation around each axis that each image had to be rotated, again, to match our reference. So you can see that the maximum amount of translation was about 0.6 of a millimeter in the Z direction, and the maximum amount of rotation was about 0.35 degrees in the pitch, which is sort of the nodding direction, the nodding rotation. So you see this particular person did really well. It was a fantastic participant, and they didn't move very much over that 10-minute period, I think this particular one was. So what we've done is we've realigned all of our data. Now you can imagine if you were going to try to look at two images, maybe the first one and the last one, after they've been, or before and after they've been realigned, it would be really difficult for, certainly for me, or for most people, to see a 0.3 millimeter translation between the two images. So we've realigned our data. It's all nicely lined up so that we hopefully now know that if we click in a single voxel in a particular part of the brain, then we'll be looking at the same location in every single time point along our time series. So the next step is to then look at co-registration. So realignment here, we were looking at the same type of image, but it just translated over time as the person was moving. In this co-registration step, that looks at two different types of image from the same person. So we've got two types of data. We've got a structural scan and we've got a functional scan. So here we're going to co-register those two things together so that we can use the structural high resolution information in the structural scan to help us with one of the steps, one of the following steps in the processing pipeline. Now at this point, I've got to look at my cheat sheet to make sure I get these things the right way around. So I do co-register and estimate. Okay. So again, it's the same batch editor, a different set of instructions, or different set of options, I should say, down here. And here we're just going to estimate. So we're just going to estimate the translations and rotations that are required to match our T1 scan to our functional data. Okay, so our reference image again is telling us there are two things we need to fill in. You just click mean in this particular case. This mean image is created in the realignment process, and it just creates a mean of the 256 sets of data. In this particular case, we're not really interested in the change in signal. We're just interested in reducing the noise in here. And our source image is going to be our 3D T1, or T1 scan. Just click in there, and click done. Okay, so I've been talking for half an hour, give or take. Does anybody have any questions at this point before I do a little bit more? Is anybody actually following along with this, with their own data, or is everyone just listening to me? And
yes, Dr. Gordon. Hello. Yeah, I'm following very well. Thank you very much.
Good to hear from you.
Following from Saudi.
Yes.
That's fine.
Oh, so is it Martina's following? Anyone else?
Yeah, I'm following with your data.
Excellent, thank you. That's if I'm going too fast, anyone just let me know and I can backtrack if anyone's getting stuck. It's not working or it's all gone horribly wrong, just let me know. So we're at the co-register stage. So what we've been asked to do is to provide a reference image and a source image. So what this tool, this function is going to do is it is going to take our 3T scan and it's going to find out the parameters required to make it co-register with our mean functional image. Okay. So it's going to find out all the translations, rotations, and in this particular case, also zooms, because the resolution is different. And to match the resolutions, we need to use a zoom function. So again, we filled in the two requirements. Not going to change anything else in this particular case. I'm just going to click the green go button and you'll see a whole bunch of various things flashing up in the bottom left-hand side of the screen. And you'll see that there's a function been compared. It was quicker than I was expecting. So what we've done, what the computer has done, is that it has co-registered, as well as it can, our structural data, which is on the right-hand side, with our functional data, which is on the left-hand side. So in this particular case, because we chose estimate only, we haven't actually created a new image of a new version of our T1 scan. All we've done is calculated the transforms that are required to match this image to this one. And SPM is now showing us the original functional data, that was our reference, and our source image, which is our T1, with those translations and rotations and zooms applied. So if you remember earlier, we were clicking around in the image and the two T1 scans to see if they were, and a lot of you noticed that they weren't co-registered properly. The positioning within the frame was different. So here we can actually check to see if that's this co-register function. It is designed to make sure that our two files, our two images, are positioned within the frame exactly the same. So we can click around in either of the images. And so, for instance, if we click on the right-hand side of the image in the functional data, we can see that we're nicely lined up with the right-hand side of the structural scan. If we then do the same thing on the left-hand side, we will see that the blue cross follows in both sides and lines up. If we click on the front, we'll see that they're more or less lined up. Not quite so good at the front. That's because there's a big space, a big air pocket here in your sinuses. That causes some distortion in the functional data. So it gets distorted. It's not because suddenly I had a large section of my brain disappear. It's because there's a distortion in the image that's inherent in the kind of scan that we're using here. So you can click around, look at various parts of the brain, see if they line up or not. Again, using our same functional tools, our co-register tools. And so you can see that they all line up reasonably well. Up at the top, it uses something called normalized mutual information. I won't go into that, but if you squint really hard, the final joint histogram is less complex than the original joint histogram. It's really difficult to tell in this particular case because the functional data is quite sparse and quite a low resolution. So far we have realigned our functional data so that we now have them all nicely lined up, stacked on top of each other, so that we can look at a single location down through the time series. We've matched our T1 scan to our functional data. And now we're going to do something with the functional data. Remember I mentioned looking at the structure within the structural data, so differences between the grey and white. Now we're going to use maybe not now, maybe in 5 minutes time, 10 minutes time. I think 3 o'clock is a good time for a comfort break, certainly for me, a good time to go and make a cup of coffee. So I suggest, mostly for my throat and my larynx, that we have a 10-minute break. Let's make it 12 minutes. If everybody's happy, we can come back at 3:10, and I will talk about the next part of the process. If anybody has any questions, feel free to pop them in the chat. I will endeavour to answer them while the kettle is boiling, if that's okay. Unless anyone is desperate for me to finish and keep going. I don't see anyone. Okay, so I'm going to disappear off and put the kettle on and make a cup of coffee. And I will be back in a few minutes. I'll not speak for until about 10 past or thereabouts, if that's okay. I'm taking no comments as a yes, so I will see you in a few minutes. Hello. Everybody's suitably refreshed with caffeine. All your other drinks of choice are available. Excuse me. So we got to, where had we got to? We've done our co-registration. So since we've got a few minutes to digest, does anybody have any questions at this point? Everybody happy with what's been happening? Sounds like it. Don't hear any grumbling, don't see any sad faces in any of the comments.
I have one, if I can.
Of course, yes.
So I guess you would do that process for each patient, is that right?
Yeah, that's correct. Yeah.
I'm trying to unraise my hand. I'm not able to, but it's okay.
Yeah.
Is there a way, so how long would it take normally to process one patient? And so from a clinical point of view, how long is the process if you have to do it for, 10 patients, 20 patients?
Oh, that's a really good point, and I might defer your question to I can answer the how long. So each one of these tasks so far has taken about a minute, give or take. So the realign took about a minute, the co-registration took about a minute. The next step that we're about to do, there are two variations. One of them that I'm about to do, no, not the next step, the step after, the normalized step, which would be the second from last step, we would only do if we were looking at a group of people. So instead of individual patients, say we were looking at a group of participants, let's say that had, I don't know, autism, and a group of participants that didn't have autism, and we grouped everybody together. So we'd have to do all of these steps, these first level steps for each person. So if we package all that together, it's 5 minutes per person, obviously dependent on your PC. Multiply that by 20. That's how long it would take to. So, but that's only the functions themselves. That doesn't include the clicking in between.
Okay.
So, so what I always recommend is that when you start using SPM, always do it like this, clicking through the buttons by hand, because a bit that I haven't showed you, and I'll show you a little bit, I'll maybe show you in the next section, is that you can actually create a script from the batch editor. It can create a script, MATLAB script, that you can then run for each person. So you can just create a loop to run that section within the script. It depends on how you want to do it. I would always say at the beginning, do it by hand so that you understand what you're doing.
Right.
And then once you get a bit more proficient, then you can create a single script that will apply all of the steps one after the other to all of the patients or all of the participants one after the other. So there is a way to create a script to do all this.
Okay, and you can run that so you will leave that running in a machine, or like a desktop machine dedicated to that, or you use maybe clusters or
whatever you want. It's entirely up to you. It's most of these they will use. Not all of the functions are designed to use par4, for instance. Some of them are. Some of them are designed. You can. It will, if you have a number of workers set up in your MATLAB environment, it will use it. If not, obviously it won't. So you can set it up wherever you want. It's not actually, well, again, it depends on your machine. But yes, if you have MATLAB and you have MATLAB workers available, SPM will try to use them if they're there.
Okay, makes sense.
Okay.
Thank you.
That's okay. I will come back to the question about batching and things at the end of, just so that you can get a feel for how it works. Okay, but that was a good question about, because it can take quite a long time just clicking through all of these things, but as I said in the beginning, do it by hand, because then you know what you're doing. Okay, so anyone else got any other questions at this point? No? Okay, so the next step in the process of following through essentially following through a recipe that you would apply to each of your data sets as you're going. So the next one is segment. So what segment does is it takes our structural image and it divides it into a series of separate images where each one has information about grey matter. There's a little box down at the bottom of the batch editor that tells you grey matter, white matter, CSF, bone, soft tissue, and air and background. So essentially it's using the signal intensity of the structural scan and some information about normal anatomy. It divides our scan into a series of 6 new scans, new images, I should say. So what we're going to do, again, we've got a cross where it's telling us we need to fill something in. So here I'm going to click on volumes and then specify. And I'm going to pick the 3T T1 image. I'm going to pop it in there. And then here, where it says save bias corrected, we're going to say yes, save bias corrected. And all the way down at the very bottom, we have something called a deformation field. And we're going to choose forward in that case. So what's a bias corrected image? Well, in our structural scan, there's a little bit of one just down at the bottom of the screen here. We would expect all of the white matter to have the same brightness or the same signal intensity, no matter whether we had white matter at the front or at the back. And the same for the grey matter. Grey matter is grey matter. It should be the same brightness wherever we look. However, MRI scans are usually not that uniform in terms of signal intensity. They often have low frequency changes in the signal intensity, either going front to back, left to right, top to bottom. So you'll often find that the white matter has a different brightness in different parts of the brain, depending on where you're looking. Part of the process of segmentation is that this bias, this signal bias, gets corrected. And by choosing save bias corrected, it's going to create a new image with that variation in signal intensity removed. It's not, it's a change in signal that's been imposed by the scanner and the way the data is collected rather than by the physiology of the patient or the participant. The deformation fields, these are the transformations that are required to map our structural scan to a tissue probability map. Now, I mentioned that the segmentation works on the signal intensity, So it takes all of the areas that are similar in brightness to CSF, to white matter, let's say, and designates them to be white matter. Takes all of the regions that are grey and designates them as grey matter. But it doesn't just work on signal intensity. It also uses a probability map, which is basically built up from a large number of data that was collected a number of years ago, and they created a normal template. So they averaged lots and lots of people's heads together to create this template map. And so the probability is that on average, what is the probability of this location being grey matter in our template? And it compares that with what's actually happening in our individual. And then it decides on the probability of a particular location being grey. So it has a probability map from our template plus the signal differences within our individual, and then it creates a series of maps, a series of images that describe the probability of a particular area being either grey matter or white matter or CSF. So the deformation field down here is just we are saving the information that maps our structural scan to our template. It's just like a co-registration step that's built in, and we save that deformation field so that we can use it again a little bit later. So segmentation is going to create a series of images where each one is a probability of the tissue type being in that location. So again, we filled in the cross. So now we're going to click on the green arrow. And again, it's going to do a whole series of things that will move more or less quickly, depending on the speed of your computer. I really need to know what all of the various graphs are. They're part of the process of taking our structural scan and comparing it to our tissue probability maps, and then deciding on, for each voxel in our structural scan, whether it's grey or white matter, based on what we know about the average population, what we know about this particular individual, and then creating a new image to display that. This one usually takes a bit longer than the other steps that we've done before. You might notice over on the far right-hand side, sorry, the far left-hand side of my screen, that some new images popped up. Each one of these has a C1, a C2, a C3, a C4, and a C5. Each one of those are the new images that have been created, and each one has one of the particular tissue types. So C1 is I don't have my list here somewhere. C1 is the grey matter of our individual. C2 is the white matter of our individual. C3 is the CSF of our individual. So it's still doing something in the background. Okay. I think it's done. The segment doesn't pop up any images for us to have a look at. So what we're going to do at this point is go back to our check reg button, and I'm going to select a few images this time. I'm going to select our original structural image, and then I'm going to select the C1, C2, and C3. Excuse me. So we have now 4 images. If I click done, what we'll see is that they've all now popped up on the screen. So we have our original image. We have in the top right, we have the data that the software believes is grey matter. We have the data, the locations of the where the software believes is white matter, and then we have CSF as the 4th version. So again, it's always good to check to make sure that these things have worked correctly. So one of the best ways to do it is to find a bit of brain that you know is a particular tissue type. So let's click the brain stem. We know the brain stem should be white matter, because it's the bit that connects into your spinal cord and connects up into all of the white matter in the rest of your brain. So in our white matter image, you can see that it's bright. So that has a very high probability of being white matter, which is good because that's the brain stem. If you look in the grey matter image, we can see that it's black, has a very low probability of being white matter, which is also good. And then if we look in the CSF image, we will see that, again, it's black because it's not CSF. If we check the corpus callosum, which is the white C-shaped bit, that's basically the connections between the left and right hemispheres of your brain. Again, we can see it's white it's bright in the white matter image. It's dark in the grey matter image, and it's dark in the CSF image. Just to make sure that we're not seeing anything that's particularly biased, let's look in the CSF, let's look in the ventricles. So that should be no grey matter. Again, where the cross is in the top right, we see it's black. We see in the cross in the bottom left, we've got the cross in a black area. So there's no grey matter, no white matter, but there is CSF in that region. So we're clicked in an area of black. So our software has segmented, has taken our full structural T1 scan and it's divided it into grey matter, white matter, and CSF. And it's also remembered the translation from our individual participant to that standard template that I mentioned. That standard template that's been built up and averaged over 351 individuals, or however many it happens to be. That's important because that template gives us a standard anatomical map that we can use, and it's the same standard anatomical map that lots of other groups use. It came from the Montreal Neurological Institute, where they took lots of people, averaged all of their data together. I'm saying average, it wasn't quite what they did, but they pooled lots of data together from lots of people and created a standard template. And not only SPM, but lots of other software that do similar things use the same standardized template. And that means that it's like having a standard set of longitude and latitude coordinates to be able to navigate around the world. Everybody uses the same mapping system, uses the same GPS coordinates to locate an individual location on the 2D surface of the Earth in SPM and generally in computational neuroimaging. If you're comparing groups of people, you will match everyone to this standardized template. So what we have is our segmented data, but also the mapping from our patient space or participant space to the template. So we have that mapping from our structural image to the template space. Now we need to apply that same mapping to our functional data, so that our functional data can be mapped from participant space again into template space. Template space is important, as I said, because it allows us to compare our results with other people. If we're all using the same map, then we can all navigate to the same place, or we can all check that the activation that I find in my experiment is similar to activations that another group has found using a similar study paradigm, for instance. So in order for us to do this group normalization, remember, so far we've always been working in the patient space, the participant space. So the data has always been essentially as it came out of the scanner. Now we're going to transform that functional data so that it now matches our template. And let me just again pop up my cheat sheet. And okay, it's just right this time. Okay, so normalize and right. You want to do a new subject. Just to come back to the question earlier, if you had lots of people, you could always just do another subject, and you could put in two sets of data. We've got subject 1 and subject 2. Won't. What I'll do is I'll get rid of subject 2, so we're just back to where we normally are. So you could have lots and lots of different subjects, and then apply each individual deformation field to that individual set of data. Okay, let's just continue with the simple option first. We've got our deformation field that's been created by the software, and it automatically gives that a Y at the beginning of its file name, so it makes it relatively easy to find. Click on that one, and then click Done. Our image is to right. So remember, we want to apply that deformation to our functional data. And you'll remember before we had typed inf into the frames in here. Okay, but that, in this particular case, that gives us lots and lots of different images. To make things a bit simpler, we can use the filter, and I'm going to use hat F. So that basically says filter, I only want files that begin with F. Before, if we didn't have the hat symbol, then that F could be anywhere in the file name. Here we're being specific and saying I want all of the files, all of the frames that are within a file that begins with F. So if I do that, it's simplified everything. In our file list, again, I can then select all, and we have our 256 functional images. So At this point, we have a write command. So what's going to happen is that this deformation field, so this is the set of instructions that matches our structural scan to the template. And you remember we did a co-registration step before that, which matched the functional data to the structural data. So essentially here we are taking this deformation field set of instructions and applying it to our functional data, as we have down here. So that is then going to match our functional data to the template. And it's because it's a write, it's going to create a series of new images. And each one is going to be have a voxel size of 2 by 2 by 2 millimeters. If you wish, you can change that to anything you want. Change it to 3 by 3 by 3, or whatever your particular want. Usually, unless you have a particular reason to change it, I usually just stick with the default values of 2 by 2 by 2. Again, you'll notice the X's have gone, green arrow is back. So it's now going to write out a series of images that correspond to our original functional data. These new images will be changed in that they will now have the same dimensions, the same voxel size, and the same resolution and the same location within the frame as our template. So this takes a little while, so it's just writing to disk, creating a new image. Okay, so it should have done what it was supposed to do. So what we can do now is we have the final step of the pathway of the pre-processing is to then smooth the data. So we have, again, images to smooth. You specify. So what we want to do is we want to smooth the functional data that we just normalized. So we now have a new file down here that has a W at the beginning. W, for whatever reason I don't understand, is the prefix for the normalized data from our normalization process. We still have the original file up here, fMRI, fMRI.ni, (1). Here we have the normalized version that we created with the normalized write statement. Again, we can simplify things by putting a hat W. So that tells us there's only one file that begins with W. We want to smooth all of the files, all of the frames, within that file. So we'll use the inf frames again. So we now have our list of 256 individual frames. Select all and click done. The default full width at half maximum is 8 by 8 by 8. So let's just put a comment asking if I'm meaning warp. Yes, that was the word I was looking for to describe the process, but it just wasn't coming. Thank you. So we can change the default smoothing to whatever you want. There's no, in this particular case, there's no justification for me choosing 6 by 6 by 6, except that that's what's in the SPM manual. I usually use 8 by 8 by 8 if I'm doing it. There are reasons that you might choose a different smoothing filter dimension, full width at half maximum. Has to do with things like matched filter theorems and the size of the regions that you're expecting to find. It's probably not enough time to go into that today. So smooth, relatively simple. Pick the images you want to smooth, pick how much you want to smooth them, and then click the green for go button. And as before, over on the left hand side, you'll notice that there's a file swfMRI.nii, smooth normalized functional data. And again, this is a write process. It's creating new data, so it takes a bit longer than the processes that we're doing before. You always want to minimize the number of write steps that you have in your pathway. Every time you write out a set of data, every time you apply an interpolation, you're losing data, losing information, I should say, not data. And you're losing information, mostly high frequency spatial information. So the interpolation tends to smooth out sharp edges. So let's have a look at what that smoothed image. In fact, let's compare the mean image with the normalized image with the smoothed image. This might not work, but we shall see. Okay. So we've got the mean image, which maybe looks slightly better. That's the original image, and that's the smoothed image. You can see they still don't look particularly great, but remember, the functional data, its role is to give us information on changing signal intensity, not structural information. So we've gone through a series of spatial pre-processing steps. These steps would be routine for in the order that I went through them, would be a standard processing pathway if you were doing a functional imaging, if you were analyzing a functional imaging data set. The bit that comes next, the model specification, that's going to be very much task dependent, or dependent on your experiment that you're going to be doing. So I think for the next few minutes, I'll sort of come back to Martina's question earlier, which was about what happens if you've got lots of data that you want to process. And my answer still stands that if this is the first time that you're doing it, I would certainly recommend that you go through the individual steps by yourself. You click the buttons in order, and you make sure that you have a basic understanding of what the buttons do. One thing I pop the batch editor back up. One thing I didn't point out, and maybe I should have, was that once you've input all of your data and you have the green button, what you can do is you can save it. You can save this set of instructions. You just clicking on the floppy disk button, and I did it earlier. I saved each one of the steps that I was doing. So let's imagine that you want to repeat the realignment of your data of that particular individual. Click on so that's save a job, so you can save it, you can change the name to whatever you want, store it in a location that's beside the data. If you want to repeat the process, then you can just simply go back to your folder of jobs, open the realignment, and it will repopulate this with all of the information that you put in before. So if you save this for each individual, you can always go back and rerun the process, or you can go back and fix any mistake you might have made and rerun it without having to try to remember all of the various options that you might have changed. I would certainly suggest saving as you're going. One of the other useful tools is that you don't just have to do these one at a time. When we were going through the steps, I was picking them individually from the user interface up here. What you can do is, once you have the batch editor open, for instance, and you've set up the first step, what you can do is go up to the SPM tab up here, and it will then say you've got some options: temporal, spatial, statistics, etc. If you go into spatial, you will find all of the same options that you have on the main window. So you could pick co-register estimate, and then you'll see that this now looks the same as the estimate option by itself. What you can do, if you remember, when we did the co-register the first time, we chose the mean image that was created from here, mean image only. However, if we're building it beforehand, then we don't know what that file is going to be called. However, there's a useful button down here called dependency. If you click that button, it gives us the option of choosing the mean image created from the step before. And our source image, here, still have to choose our 3TT1. So now we have two steps, and if I was to click the green Go button, it would do the realignment and then move automatically onto the estimate job. But if we've got those two in the list, then we can go on to the next step, which was segment. So we can go on to segment. It's going to ask us for a volume. Remember, up here, we're going to be changing the T1 because we're co-registering it. So our segment volume, we should click on dependency and take our co-registered image. Again, we did save bias corrected. Then down at the bottom, the forward. So now we've set up our 3 steps, one after the other. We can just keep going, and then our next step is right. I also think about that. Data, got a new subject, deformation field. So that deformation field comes out segment. So we can click dependency, and we've got forward deformation. And our images to right, those are going to be our functional images. So those ones, remember, we have to specify. So we need hat F and then inf in there. And we can select all. And then just to finish it off, we can put in the smooth at the very end. We want to smooth the output from the normalization step, and then change our smoothing parameter if you want. So instead of having all of those things, all of these steps individually, we can create a pathway that will be identical. And then see if we can save it. It happens to be in jobs. I'll just call it something very unhelpful called all. And that we have some data to enter there. We probably have some data to enter here for our T1. And then we will step through all these processes, go through the whole processing pathway, and then the output will be our smooth, normalized functional imaging data. That's good. That means we can do all of these steps one after the other for one single individual. There is another step that you can do if you want to, if even this is too much work, and you really want to go to the MATLAB script route rather than using the user interface. You can save the batch and the script. So the batch essentially is this list of instructions, and the script is a little helper script that you can just put into your own MATLAB script, and it will then do it for you. Let me just say all script. All script. So it automatically opens the script in the MATLAB editor. So you can, for instance, create a loop. Well, it's created the loop for you already. So you have for C run equals 1 to n run. That loop there can be, you can, depending on how you set it up, you can use that to populate a whole series of different patients, participants. And you can use this script. If I just open that one. So it creates 2 files. One is the script, which has a little loop, and the other is the job. The job file is basically what we see in the batch editor. It's the list of instructions, the things that we want to do. And they're all, it's all been pre-populated. So I'll have lots of information in there already. Excuse me. And lots of the options that are in the batch editor have been copied into this essentially another MATLAB script. And we see we'll have our 3D T1 full path file name, etc. So we've got lots of, if you want to go through the MATLAB scripting route, then you can, this will give you some basic information that you can then use to create your own script. Okay, I think at this point I'm going to stop sharing, and yeah, and then redistribute my Teams window, and I'm going to say that, as you can probably hear, my throat's getting a bit raspy. That means at least I've reached the limits of my talking capabilities for today. So I would just like to see, does anybody have any final questions? What I will say is this has been quite a whirlwind tour of a small proportion of what SPM can do. There are lots of other powerful image processing and image analysis tools built in to SPM, and I don't know what Amir's thoughts are for the next few lessons, sessions, but I might be persuaded to talk a little bit more about SPM if that's what anybody wants. So.
Hi, I do have a question. Sorry,
yeah.
I can't use the chat function for some reason. And I don't want to tire your voice too much. Thank you very much for your time. That was brilliant. Because I've never really seen that before at all. What I was wondering was, what is the basis for doing the registration? When you're registering a given person's scan onto the standard, how is it doing the matching? What's the basis for doing it? Because brains vary so much.
It's the basis for this is a global matching. So it's matching essentially the global size and shape to the standardized template. That's a really good question, and a really good point is that it just matches the global shape. There's still an awful lot of inter-individual variability. One of the reasons for doing the smoothing is to smooth out some of that inter-individual variability. There are tools out there that can match, that do sort of sulci matching, where they're much more computer intensive, right, essentially. But in this particular case, because it's functional data, which is quite low resolution anyway, it works on a global perspective. So there is still lots of variability left there. Thanks.
Right, so it's just the kind of overall brain volume, and it just tries to match that.
Yeah, exactly. Yeah.
Okay, that makes sense, because I was puzzling about how on earth it would do it. And I've always puzzled, because I knew that SPM kind of does this, and thinking, and how? Yeah. Right, that explains it. Thank you.
Yeah. It has 12 parameters in its transformation, basically. Right. Translations, rotations, zooms, shears. So basically, yeah, it gives you 12 relatively crude normalization.
Okay.
Sure. Anyone else? I've got a question from.
I have, yes. I know that you are. You said you are tired of talking. You reached your. It's a very quick one. I think. Well, thank you very much for the entire showing the entire workflow. That was really interesting. I wanted to ask you if that type of workflow is actually used in any sort of clinical environment, or you normally do just in sort of research cases.
One of the caveats of SPM is that it says in the sort of free license thing is that it's not clinical. It's not clinical software. It's not. It's research software. However, that doesn't mean that you can't use it in a clinical setting. And I have done. I've used it in patients that have been going for neurosurgery in terms of looking for their motor areas and eloquent areas. So it has been used with very strong caveats to the surgeon that this is, and it's never it's always done in a sort of an MDT setting with a radiologist, a physicist, a neurosurgeon, often a psychologist, depending on what we're looking at. What you find now is that scanner manufacturers have figured out that this actually is quite useful, and they will build in to their CE approved software similar versions of this that don't have the normalization to the template stage, because we're only really interested in the patient data. We don't care if they are how it fits to the normal template. So we most manufacturers now have a system that's built in that allows you to do simple on-off type experiments.
Okay.
SPM is far more flexible, and it lets you do different kinds of experiments, etc. But it is very much a research tool rather than a clinical tool.
Okay, thank you.
Amir has a question, but he has to disappear at 4, I think. A reviewer has asked me to explain whether I have done anything about head movement. I followed the very same steps using CON. Do we still need to worry about head movement, or do we need to go into depth and correct for that? Head movement's a really interesting topic, and probably a whole other 2-hour discussion about head movement. The thing about the scans that you use for functional imaging is that, I think I mentioned, there are distortions due to how the data is collected. It changes the shape of the brain. Your realignment stage basically simply rotates the brain image to a reference. However, the angle that your sinuses are, the brain is within the magnetic field of the scanner, can change the signal that is detected. So the signal is also a function of position, and the signal doesn't get corrected when you're doing the realignment. It's only the shape or the position within the frame that gets corrected. So it's not as simple. It's not as simple as simply correcting the location within the frame, because there is also the possibility that the signal is a function of the position also, which is another potential set of. And in CON, which is another toolbox that Amir mentions, you can use those movement parameters as nuisance variables within your statistical analysis. So it is possible to correct it that way. But yeah, that's a big question. I think I'll talk to Amir offline, because that might take another half an hour to discuss that one. Okay, anyone else with any questions? If anybody does suddenly come up with a question or wants to know a bit more about SPM or anything else along those sorts of lines, feel free to drop me an email. My email's in the invite and the original flyer that Amir sent around, and occasionally I lurk in the background of these sessions, so feel free to reach out if anybody would like any more information or a bit more of an in-depth tutorial or discussion about SPM or any of the other flavors of toolboxes that are out there. Okay, if everybody's happy, I don't see any other questions. I think I'll wrap up in 4 minutes. 4 minutes over my 4 o'clock deadline. So thanks for your attention, everybody, and the questions and the comments. Always helps when you're on this side of the screen to know that there are people listening. I always get paranoid that everybody's run off and have just left their teams switched on. So thank you very much for being involved, and goodbye.
Bye.
Bye-bye.